the endoderm called the pericycle. I'll come back to that a little bit later. And so this procambium, which is primary meristem in the apical meristem of the root, will eventually give rise to the stele, which is composed of vascular tissue, xylem, and phloem. Here's a cross, sort of a cross of the xylem. Look how thick those cells are of the vessel elements, and those are because they have a secondary cell wall, sort of forms like a cells radiating like this, and then the phloem cells are right over there. Notice here, do you see here in the endoderm? Do you notice how these cells are a little red right in here? They're red because they're producing this wax that surrounds them, called the Casparian strip. I'll come back to this later. It's really cool. It prevents fluid from passing into the stele that is not wanted. In other words, there could be some toxics in that fluid that's moving in between plant cells, and you don't want that to get into the stele. So this is sort of the elevator of the plant, if you think about it. And so I like to think of it as like you're entering a building. First thing is, it's hard to get into the building because of security, for example. Number one is the epidermis, so it's not going to let anything in. And then if you do get past that, you can move through number two, which is the cortex, or ground tissue. You can sort of go in between cells. If you travel through a cell, you'll have to go through the membrane, and of course the cell membrane is selective, so if you're unwanted, you won't be able to get in. But you can pass on the outside of cells. But you're not going to pass through the number three, which is the stele. That inner layer right in here called the endodermis has that Casparian strip, which prevents that. So this cross is the xylem, and then over here is the phloem. So vascular tissue, ground tissue, dermal tissue. This is the root, the dicot root. And the dicot root is known for this sort of cross shape. Here's the endodermis, the pericycle, which is this one cell layer underneath. Here's the xylem, here's the phloem. Here's the cortex, so it looks like it has the measles, which are little visoplastic structures. Found this picture. This one's really cool too. You can see here, this is a nice shot of the stele. Notice here that you have your xylem here, and then just on the outside of that is this pericycle, and then just on the outside of that is the endoderm in purple, endodermis, right there. That's kind of neat. Here's the root cap, apical meristem. Real close up of this. Here's the endoderm. Let me highlight it. Here's the endoderm cells right here that go around. One can say that the endoderm is considered technically the innermost layer of the cortex. And then you have this pericycle. And it's like, Anne mentioned that before with the story. It's this cell layer just on the inside of the endoderm. And why it's significant, I'll just mention it now, is that these cells are capable of division. And if they're capable of division, what can happen is they can bust through the endoderm, and it can actually form a lateral root. When I say lateral root is when you have like branches coming like this off of roots. So how do those branches form? Well, they form when the pericycle becomes meristematic, and it starts to penetrate through the endoderm and through the cortex. And so there's endoderm, pericycle, phloem, and the xylem. Notice how thick the xylem is with the secondary cell wall. By the way, what cell type is this? It's sclerenchyma, secondary cell wall. So this is I like this picture a lot. This is a sort of comparing and contrasting what a dicot root looks like. Dicot root is what we've been looking at primarily. We've been looking at the xylem, which is across here. Here's the phloem, which is in between. Here's that pericycle I was just talking about it, and then the endoderm, and then the cortex, and then the epidermis, like this. But then in the monocot, like for example in grass, fibrous roots of grass, what you're going to see is it's not going to be a cross in the center of the stele like that, but instead the xylem are going to be in these little bundles right in here, and the phloem is in between the bundles, and then you have this little region in the center called pith, which gives them support, the type of ground tissue, parenchyma cells, pith, which provides some support for the root, and then here it has cortex and epidermis. So take a look at the real monocot root. So here's the real monocot root. Dermal tissue, ground tissue, vascular tissue. And notice how the big circles right here are the xylem. All these little cells in between are the phloem, and it has this pith area. Here's a picture of a branch emerging. Again, monocot roots. The xylem cells are a little thicker. You can see here, phloem is all in between. Right in here is the cortex towards the outside, the pith could be on the inside. Here's a real close-up of the endoderm right in here. Here's the pericycle, the cortex over on the side. If I were to ask you, like, what is that? You'd say, oh, clearly that is a cross-section of a root. That's clearly a dicot root. This is a close-up of the stele. You can notice here the endoderm is highlighted in red. And you have the pericycle, which is this one cell. Here's the phloem and the xylem, and it has the cross. Now, this is a great picture showing side-by-side dicot and monocot. So again, here's the cortex, here's the dermal tissue, here's the stele, xylem, phloem, etc. Then over here, dermal tissue, cortex, and then you can see the stele located here. You can see the endoderm is highlighted in red because it has that Casparian strip that stands a little darker. These bigger circles are the xylem. You can see that? Right there, the bigger circles, and then the pith is on the inside right there, and then here's the phloem. So I was alluding to this before, like if you're going to produce a lateral root, in other words a root that's coming off the side, you got to bust, it's like sort of breaking through, you got to bust through the epidermis, you got to emerge through the cortex, And so where does the lateral root originate? Where does it sort of spring from? It springs from the pericycle layer. Those cells become meristematic and they start dividing. Not only do they become meristematic, they're the primary meristem, so it's going to become protoderm, Cambian, and ground meristem. So this root is going to have its own ground tissue, its own epidermis, and its own vascular steel right there. And so let's draw our attention now away from the root and look at the shoot. And so if we're talking about primary growth in the shoot or the stem, where's it going to be? It's going to be at the tippity top. So this is the, I don't know what this looks like to you, like some house right here with the door, but basically this is the top, the apical terminal bud of a shoot. So in other words, these are the cells of the apical meristem that are dividing, mitosis, mitosis, mitosis. And what do they make the three primary meristems, same as in the root, thank goodness. So in other words, the protoderm will eventually become the epidermis of the shoot. The ground meristem will eventually become the ground tissue, and the procambian will eventually become the vascular tissue. And so if we take a look at this meristematic region, this apical meristem, you don't need a root cap, but this apical meristem up here at the very top of the plant are the cells that are dividing. And so, as I mentioned before, let me just say it again if you don't mind, just for clarity, the primary division of a plant for growth, primary growth in an upward direction, the reason it's going upward is because the cells are pushing down, so it's going up. Right here. What you got is protoderm, which is eventually going to become the dermis, procambian, which is eventually going to become the vascular tissue, and ground meristem, which is going to be the ground tissue of the root. So these are three primary meristems, and they're at the tippy top of the shoot. And so this is a stem. So if you take a plant, an herb, I know it's an herb, it's not a woody because it's not very thick, but if you cut a stem in half, this would be a typical monocoque over here, and this would be a typical dicoque over here. There's some differences. One of the things that you're looking at is this vascular tissue, and these vascular bundles. You notice here, these vascular bundles in a dicoque are around the perimeter of the stem. This is, again, tippy area in the center, so they're around the perimeter like that. Whereas look here in the monocoque, the vascular bundles are sort of scattered throughout the stem. You see that? Now, I wish you had higher magnification, so yes, I agree. So here's the dicoque, here's the pith in the center. What's the pith doing? It's providing some strength and some stability along with the cortex. The cortex is not so much a function in the root as storage, but it provides strength. So the cortex, if you remember this, is made up of chlorenchyma cells, which have a little bit of a thicker primary cell wall. If you look close at one vascular bundle, you'll notice how the xylem is more towards the center, and the phloem is a little bit more towards the outsider cortex. So you got dermal, ground, vascular, ground, right in here. And so this is a dicoque. Again, the dicoque, and here's the monocoque. Notice the vascular bundles are sort of spread out in between. So dicoque, monocoque. Here's a close-up of the monocoque stem. The monocoque stem has these little vascular bundles. But what's interesting is Douglas, I guess, trying to be funny, maybe. I call these vascular bundles little monkey faces because they look like they have eyes and a little bit of a nose, looking like a monkey, maybe. Here's the eyes right here, the monocoque stem. These are obviously the very large xylem vessels. Notice how thick they are. They carry water. Here's the phloem. I like this picture a lot. Look at the sieve tube members, which are also hollow, but then they have these little companion cells, which are really helping out right there. This doesn't have a large amount of cytoplasm right there. So this is a close-up of a vascular bundle of the stem of the monocoque. And then getting to the leaf. The leaf has this upper area right here, which is dermal, and then it has this ground tissue, which is called the middle or mesophyll. The vein is not shown in this picture. It has this waxy cuticle. And the epidermis, a single cell layer, sort of like a puzzle, is the first line of defense against pathogens, and also the cuticles to prevent water loss. And so what's fascinating, you might be familiar with the leaf from photosynthesis, but if you look on the underside of a leaf, you'll notice that there's these specialized cells that flank these pores called stoma. These specialized cells are called guard cells, and they're capable of photosynthesis and opening and closing. They swell open, which allows carbon dioxide to come in and oxygen to leave. And so here we have is the dermal tissue, and then the yellow is the ground tissue, and then we have more dermal tissue here. Now, where's the vascular tissue? The vascular tissue is right here. We call it a vein. And the vein is made up surrounded by bundle sheath. If you remember that, the bundle sheath cells that surround the vein. And then inside we have the xylem, which conducts the water to the leaf, and the phloem, which conducts the sugar that's being produced in photosynthesis, dissolved in water, away from the leaf, down the petiole to the stem, and then ultimately the root, or it could be to a fruit. And so again, we'll talk later about how guard cells regulate transpirational losses, but they do. They close up at night and they open up in the morning generally. But this is where gas exchange takes place, like these little mouths right here. So gases go in and out, and also water goes in and out. Water leaving is a good thing, transpiration, because it pulls through capillary action. That's cohesion and adhesion. It pulls water up the plant. That's how the water is able to travel up xylem, is through transpiration. And so that's providing the pull, especially if it's windy, especially if it's sunny. You have a very low water potential in the air, so the water is able to leave. What's troublesome, though, is excessive transpirational losses can be lethal to the plant, and so that's a cause for concern. And so you can see here, thermal, there's ground, and vascular in the leaf. There's the stoma, the guard cells, which allow the gas exchange, oxygen out, CO2 in. And that's the mesocell, which is ground tissue. These are parenchyma cells, these are palisade, these are spongy in relationship to the way they're close to each other, like a palisade, like a fence, which captures a lot of sunlight. Spongy allows air circulation to occur in the leaf. So it's really a cool structure. This is one of my favorite organs of a plant, is the leaf. It's an incredible example of structure related to function fossil. And then finally, the vascular tissue, I was mentioning this before, travels from the petiole into the leaf, then it goes into, it brings water to the leaf for photosynthesis, because as you know, inside the plant cell, inside the palisade, the chloroplast needs water, especially in the thylakoid membrane, in the photosynthesis in order to take place. So there you go. Dermal, ground tissue, palisade, spongy, lower epidermis. Notice the lower epidermis has the guard cells. None of these air spaces allow for circulation of gases. So I hope you enjoyed this discussion on primary growth in plants. Thanks for watching. Hi everyone, it's Mr. Cinti, and I'm happy today to be talking to you about plant hormones. That's right, plant hormones. We're not the only organisms that produce hormones, that is animals. Plants also make these hormones. They're chemicals that are capable of moving from cell to cell, and they communicate a message. So it's sort of like a chemical text message, and it's produced by one cell, and it's received by another. Usually a specific cell is destined to receive it, and then that cell does something. That cell either divides, or it grows, or it stops growing, or it dies. Something like that. There's some sort of effect as a result of it. So let's jump into this conversation. I think you're going to like it. One thing that I want to say about it is it's not so much important to recall, in terms of memorizing the names of hormones. It's great if you can recall them, but it's more of the point is to enjoy them, to understand the bigger picture. And so the word hormone itself comes from a Greek word meaning to excite or to set into motion. So it's kind of like if you think of a big chain of dominoes and you flick it with your finger, that would be the hormone to get going, to set into motion. And so hormones are pretty common in most organisms, and they're produced usually in one part of the plant, and then they target another part, as I was saying before. One of the very first plant hormones that was ever isolated, it's a pretty cool story, I'm going to actually mention it in this video, has to do with the hormone auxin. And there's actually a couple of different kinds of auxins. It's basically a growth hormone. And when you have auxin, you're capable of normal growth, and when you don't have it, you're sort of stunted, in other words, a dwarf. And so, here you have tall, short line kind of thing. And so, the chemical structure for auxin, it's very similar. This is auxin. It's also abbreviated IAA. It's very similar to the amino acid, as you can see here, tryptophan. And so one of the things I just wanted to show you what we're talking about in terms of chemical structure. Some of the hormones could be steroid-like, and some of them could be peptide-like, for example, auxin. And so just the big picture is that cells can communicate with other cells. It can be locally. Cells can produce chemicals that are secreted from little vesicles, and they target adjacent cells. This is something known as paracrine signaling. It's sort of local. And then in the nervous system, neurons don't actually come in contact with one another, but they can communicate. How do they do it? Well, in their axon terminal right here, they secrete these chemicals called neurotransmitters, and there's a bunch of neurotransmitters. Acetylcholine happens to be one of them. You should check out neurotransmitters if you're interested in that. It's the way in which neurons communicate. In other words, it's sort of like a post office where you're whispering in one person's ear and they're whispering in the next. So in other words, the brain, for example, can communicate with the foot in order to kick a soccer ball by moving neurotransmitter to cell to cell to cell to cell, and then ultimately the neurotransmitter will connect to the muscle, which is through the neuromuscular junction, which is also a synapse, and then it'll cause the muscle cell to contract. So all that is sort of called paracrine. Now, a hormone, for an animal at least, is produced by glands. Now, plants aren't known for having glands, but we have groups of cells that are specialized for secretory purposes, and so these endocrine glands secrete hormones, which are what these blue structures are. And it goes into the bloodstream, and it travels throughout the body, and it goes to a target cell. For example, an endocrine cell could be like, for example, in our brain, in our pituitary gland, and it produces a hormone that travels in the blood and goes all the way down to the ovary, tells the ovary to start developing a follicle. Or this hormone can come from the adrenal gland, and it goes into the blood, and it causes the lung and heart to increase respiration and heartbeat. And so plants do not have this blood to go into. They have instead vascular tissue. And so hormones can travel through the vascular tissue, in xylem sap and in phloem sap, but it can also be cell to cell as well through simple diffusion. And it's often long distance. We call that endocrine because it's on the inside, as opposed to a gland that's an exocrine gland. Like, for example, your salivary gland produces saliva, which then travels in a duct to the outside, which is your mouth, or the mammary gland to the outside. So hormones, chemical messages. So the research of how plants bend toward the light led to the discovery of plant hormones. It's a really cool story, as you can see here at the sun, and plants are moving towards the light. And this is an example of what we call phototropism. Tropism means toward something. It's an orientation toward, so it's toward the sun. So in order for that to occur, there has to be some bending, which occurs over on the dark side. So that's kind of interesting. If the dark side cell bends, in other words, the cells elongate, then the whole plant will sort of orientate itself towards the light. And you can actually see the plant moving throughout the day as the sun moves across the sky. It's pretty cool. And so this is what we refer to as phototropism, positive phototropism moving toward the light. You can even see it in a forest. This is a real powerful event. A forest is very competitive for light, so you got to be able to roll